we're going to take a slight detour away from R and RStudio and get back to doing some math as we introduce probabilities. Probability is the foundation of all of our statistics. When we do scientific experiments, we do the experimentations and we make assumptions. We then compare our data to the expectations based on our underlying assumptions. Our assumptions and the expectations are going to form the theoretical frequency distributions that our data should follow. If we have deviations from these theoretical frequency distributions, then that could lead us to make important conclusions to some biological phenomena. One way that helps us make these conclusions is when we calculate a p-value. A p-value is defined as the probability of obtaining a value or data as extreme or more extreme than our observed value or data if the null hypothesis is true. This is an important definition, and it's one that you should know. P-values are the probability of obtaining data as extreme or more extreme than our observed value if the null hypothesis is true. So what this is essentially saying is, based on our assumptions, underlying assumptions, how likely is it that we would get data as extreme or more extreme just by chance alone? If we obtain a low p-value, then we would conclude that the probability is so small that something other than chance is generating our results. What is that other than chance factor? Well, in terms of an experiment, it could be our manipulation. So if we grow plants, have two different sets of plants, and we grow one set in full sun and the other plant in shade, and we compare plant height, our null hypothesis, our assumption is that there's no difference, is that the sunlight and shade have no difference in growth. But and that assumption then leads us to a null frequency distribution, a theoretical frequency distribution. So if we do the experiment, we expect zero difference in height. But when we actually perform the experiment, we get a difference in height because of the effect of sun and shade. The p-value quantifies that difference and says we have a certain probability of actually observing this difference by chance alone. We'll arbitrarily set a cutoff and say if it's below some value, then chance didn't generate this difference. Something other than chance did. A p-value represents a probability. So what is a probability? The definition of a probability is the likelihood that an event can happen. We will use p of an event to represent the frequency or the probability that an event will occur. So our probability of an event is equal to the frequency of that item in our population. So consider a jar of marbles. That jar of marbles consists of red, blue, white, and green marbles. In that bag we have 200 total marbles with a distribution like this, where we have 120 red, 40 blue, 36 white, and 4 green. If we wanted to know the probability of drawing a single red marble from that bag, then the probability of drawing that red marble is equal to its frequency, which is 120 divided by 200, or 0.6. If we were interested in the probability of drawing a green marble from the bag, then that probability is equal to its frequency of green, which is 4 over 200, or 0.02. An expected value is the weighted average of all possible values. So if we made 5 draws and we wanted to know the how likely is it, or the expected number of reds in those 5 draws, then we can calculate it using this equation. So our total number of events that we have, 5 draws, times the probability. So if we were to make 5 random draws and wanted to know how many red marbles we expect to get in that draw, it would be 5 times the probability of the red marbles, which is 0.6. So we would expect to get 3 red marbles out of those 5 draws. As another example, if we drew 400 marbles out of this bag, we expect to get 8 green marbles. Do you see how I obtain that? Well, we have n is 400. Our probability of drawing a green marble is 0.02. So we expect to get 8 green marbles in our new sample. The thing about probability is that there's always an element of chance when working with them. So in our marble example, we had a bag. We had a bag of marbles and they existed at different frequencies. Just because we expect to get 3 marbles, 3 red marbles out of 5 picks doesn't mean we will always get 3 red marbles out of those 5 picks. It's going to vary and chance dictates it. So here's an example. Let's say we had that same marble bag and we did 1,000 different trials, but we changed how many marbles we drew out of that bag and recorded the number of green. And then once we had the number, we converted it back to percentages. Well, if we had a sample size of 100, so 1,000 trials of drawing 100 marbles at a time and recording the number of green, the proportion of green in our samples varies from 0 to 0.08. So even out of 100 samples, we had the possibility of getting 0 marbles. We had a possibility of getting 8 green marbles out of just 4 marbles in that bag. Standard deviation was 0.0145. If we increased our sample to 500, so we drew 500 marbles and recorded it. Now, we didn't have any samples that didn't have any green marbles. We found at least some green marbles. Probability of the green in our sample was 0.004 up to 0.042. If we increase it to 1,000, the proportion of green was 0.005 up to 0.035. In each case, as we increased our sample size, our standard deviation decreased because the probability of our actual event happening starts to approach its true value. And that's an important concept. This is why sample size matters. As our sample size increases, the actual probabilities, the actual frequencies that we observe starts to approach the true value, and the dispersion around that true value, or the dispersion around our true value, the probability in this case also decreases. So if you're wondering how I did this, I used a random number generator, the all-R multinom generator. This generates a random number from a multinomial distribution. Multinomial distribution has multiple categories, and we specify how many categories we have based on how many probabilities we give it. So if we generated a sample, it would be n, that's how many samples we draw. The size is how large of size we have, and the probability is our vector of probabilities for the different items in our sample. So for example, first one I did, if we wanted to do one draw of 100 marbles, all right, and the probabilities followed the probabilities in our bag, then I run this command and I get an output that says how many reds I have in that 100 sample, how many blues, how many greens, and how many whites. You do not need to know this function or need to know how to use this function. I just present it as an example. Probability is important when dealing with our samples. Our goal is always to get an unbiased sample. And we do that by making sure that we have a random sample. If we have a random unbiased sample, then the sampling frequencies in the data set should equal the true frequencies in our population. That means that each item is going to have the same probability of being selected, and that probability is dependent on the frequency in that population. Now, how do we collect the random samples? Well, as a review, it just kind of depends on what our population is. If we know the entire population, then what we could do is assign possible values to each of those items and then draw random numbers that states whether or not we're going to collect them or we won't measure them. If we don't know the entire population, then what we have to do is randomly select collection points using a computer and then establish grids, or pick a point, figure out a random direction, and then proceed along some sort of transect or straight line. generating a random sample in R is actually fairly easy. We have a sample function built in, and we could tell R to draw a certain number of samples from a vector or from a data set, and we can determine whether or not we draw it with replication or without. Now this is useful again if we're trying to generate a random sample because those are the data points that we're going to measure, but we also use the sampling procedure to generate a random sample of our own data set. It's a form of bootstrapping that allows us to calculate confidence intervals, especially if our data are skewed and non-normal. So to demonstrate random sampling, we're going to load in a crickets.csv dataset. When you load it in, I want you to read in the dataset as dat.crickets, so that way it matches any of the code that I give you. In this dataset, we raised 100 crickets, and we labeled each of the crickets with a number tag so that we can individually identify each one. In this population, we discovered 5 different phenotypes. Our interest is to determine the susceptibility to an infection, but we don't want to favor one phenotype over another. So if we only can perform this experiment with 20 crickets, how do we randomly sample 20 individuals so that our sample adequately reflects our population? Well, for this we will use the sample function. So we will sample from our vector, and we specify the size that we want, so how large a sample. And then we determine if we're going to sample with replacement or without replacement. So the difference is, do we put the item number back after we draw it or not? If we sample with replacement, then it's possible that we draw the same individual more than one time. For bootstrapping, that's okay, but if we do, let's say, a permutation test, that's not okay. So here we're drawing a random sample of 20 individuals. We don't want replacement because we can't perform the experiment 2 times on the same individual. So to draw a random sample, we would run this code. This code means basically draw a sample without replacement of size 20 from the ID vector in the dat.crickets dataset. So I want you to go ahead and run this, and we will see how I did it in R. Alright, so here's my RStudio. I've read in my dataset, have it as dat.crickets, and now I want to generate a random sample. So I will use the example, generate a random sample of 20 crickets. So I will do sample. We have to give it a vector, so dat.crickets, and I think we will use ID as the vector. If we look at what variables are available, we have ID and phenotype. Well, ID is the number that we gave it, so we're going to sample from that vector. We've got our sample size of 20. So we want a sample of size 20, and we want to have replace equals false. We do not want to draw a number, write it down, and put it back in, because that allows us to draw the same individual twice. Once we find the individual, we don't want them back in for that second draw. So I run this, and these are the numbers that I get. When you run it, it will be different. Think about that. Why would your numbers be different? That's because this is a random number generator. That's what we used to get these numbers, and our random number generator was based on the system clock. And it's entirely unlikely that we would ever get the exact same numbers unless we do something first. What can we do? If you said set.seed, that is correct. So if I set my seed at 2000, then I run it and run it one more time, then we will get the exact same numbers. Now, what if we wanted to increase the size? Let's say we wanted half of the crickets So out of the 100, we wanted to sample half of them. Can we figure out which half we want? Yep, we run it. And these are the numbers. Now if you noticed, the first 20 were the exact same as our sample of size 20. That's because we set the seed first, we ran it, and then we immediately ran the sample. If we did away with the set seed and drew it, every time we sample, we get a different set of 50. So the set the seed function can be useful if you want to regenerate the exact same items. So a couple things to note. When you run the sample function, x must be a vector. So if we are working with a data frame, we must specify the data $ variable name in order to sample from that vector. Also, if you're trying to do a random sample, so if you're trying to do bootstrapping or even generate a random sample for data collection, my suggestion is always to don't set the seed. Use the system clock so that way we guarantee we are always pulling a random sample. In our presentations, as we do bootstrapping and permutation tests, we'll set the seed for those examples so that way everyone's getting the exact same numbers. But when the practical application of it is that we don't set the seed. Let's now introduce probabilities and how to work with them. If two events, A and B, are mutually exclusive, then the probability that we have either A or B event occurring is equal to the sum of their individual probabilities. This is the addition rule. What this is telling us is if we're interested in the probability that A or B occurs, then what we could do is calculate the probability of A occurring and the probability of B occurring and then add them together. Now, what does it mean mutually exclusive? Mutually exclusive events are events that cannot occur together. A good example is a coin flip. You flip a coin and it's either heads or tails. The outcome of that coin is mutually exclusive. You can't flip both a head and a tail on that same coin. Likewise, if you set a trap out to capture a small mammal, you can't have that trap both with an animal and without an animal. So the outcome of that trap is mutually exclusive. But if we flip two coins and record the outcome, heads or tails for each coin, now you can have heads and heads, heads and tails, or tails and tails. Those events are not mutually exclusive. So the individual coin itself, the one coin, heads or tail, that is mutually exclusive, but once we added two coins, then you can start having these different combinations. So here are two examples using six-sided die. Our first example is if we ask you what's the probability of rolling a 3 or higher. Well, what we have to look at is first, is the outcome mutually exclusive? Could we roll a 3, a 4, a 5, and a 6 all together? No, we can't. We roll the die one time and we get one number. So we know that these are mutually exclusive events. Second, we have a probability of rolling a 3, a probability of rolling a 4, a probability of rolling a 5, and a probability of rolling a 6. Those are individual, mutually exclusive events. Each of the probabilities is 1 out of 6, so a six-sided die has 6 outcomes, and each one is 1/6 of a chance of occurring. So what we could do is use the addition rule. Probability of rolling a 3 or higher is 1/6 plus 1/6 plus 1/6 plus 1/6 equals 4/6, or 2/3. Second example, let's say we rolled 2 of these six-sided dice, and we were interested in knowing what's the probability of rolling a 7 or an 11. So this would be an example of playing craps at a casino. On your very first roll, if you roll a 7 or 11, you win immediately. Alright, so our question is, well, what's that probability? Well, we can't roll both a 7 and an 11 at the same time. So these two events, 7 and 11, are mutually exclusive. So we should mutually exclusive, and we're using the OR, so that should tell you we're going to use the addition rule. So the probability of rolling a 7 we'll have to calculate, and the probability of rolling an 11 we'll have to calculate it. Well, what are those probabilities? Well, the probability of rolling a 7 is 1 out of 36. That's if we roll a 1 and a 6, and then it's 1 out of 36 to roll a 2 and a 5, and so forth. So our probability of rolling a 7 is the sum of the different ways in which we can roll the actual 7 from those two dice. So there's 6 of those ways. 6 out of 36. The number of ways to roll an 11 is 2 different ways. So 2 out of 36. So that gives us 8 out of 36, or 2/9. I encourage you to write it out and just write down all the different combinations of rolling a 7 and the different combinations of rolling an 11, and confirm that you get the answer of 2/9. So remember, mutually exclusive events are events that cannot occur at the same time. I already gave you an example of flipping a coin. You can't get both a heads and a tail when you flip the coin. It's one or the other. If you take a 52 card playing deck and draw a single card, you can't draw both a king and a queen. It's a king or a queen, and so forth. And I have some other examples here. So the question is, could you think of other examples? This is important because when we work with mutually exclusive events, then that changes what equations we use to calculate probabilities. If we ask the OR, then we just add our probabilities together. If we have events that are not mutually exclusive, then our outcomes can occur at the same time. These could be 2 different items or characteristics, or they could be a sequence of events. So if we were interested in baseball and hitting, let's say a hit, and then strikeout, that's a sequence of events. You can't have both a hit and a strikeout at the same time for one at bat, but with the sequence of events you can have different combinations. So other examples of non-mutually exclusive events is if we looked at both sex and hair color. So the sex, male, female, that's mutually exclusive, but when we look at sex and hair color together, you can have different combinations of male, brown hair, female, blonde hair, and so forth. Age and infection status. Age and infection status is not mutually exclusive. Rolling a pair of dice, so the outcome of each die is non-mutually exclusive. And sex of offspring in a clutch of 4. That's also non-mutually exclusive. I encourage you to try to think about other non-mutually exclusive events. So, what happens if we have non-mutually exclusive events? Well, we have the same situation. We could ask the probability of having either or events occurring, which we'll get to in a bit, or the most common situation is the probability that we have 2 events occur together. So if our events are independent, but they're not mutually exclusive, then the probability that event A and B happens together is equal to the product of the individual probabilities. So what does it mean to be independent? It means that the probability of one event does not depend on the outcome of the other event. So if you flip 2 coins and you're recording heads and tails, the outcome of the first coin doesn't depend on the outcome of the second coin, and vice versa. That's independent. So if A and B are mutually exclusive, then the probability of A and B is going to actually be undefined. So it just kind of reinforces the idea that the events have to be able to occur together, because if they can't, then they're not mutually exclusive and we can't calculate this probability. So here's an example. If we have an infection by 2 different parasites, all right, so parasite A and parasite B, probability that that an individual is infected by parasite B is 0.75. That's our pink circle or our red circle. The probability of being infected by the second parasite, parasite B, is 0.5. That's another circle, and they're not to scale. Then if we're interested in the probability of being infected by both A and B, we're looking at this intersection. And this intersection is the product of our two probabilities. So the probability of being infected by A and B is 3/4, that's the probability of A, times 1/2, which is the probability of B, and that gives us 3/8. So what's the question? So what's the probability that we're infected by either A or B? Well, that's another part of it. So if we ask the OR aspect of independent, non-mutually exclusive events, then what we do is we add our probabilities together, but we also have to subtract the probability of A and B. Why? It's because we're basically going to double count. If we look at the probability of A, we have that section here. If we look at the probability of B, we include that section, and note that we've just calculated this twice. So we're going to have to subtract it. So the probability of being infected by parasite A or by parasite B is equal to 0.75 plus 0.5 minus the intersection, which was 3/8. That gives us a total of 7/8. When we work with more than two events, the same rules apply. An important one that we'll work with later on is probability that multiple events occur together. So if we had a nest that had 3 offspring in it and we wanted to know the probability of getting all 3 females, well, we need to have that first offspring female, second offspring female, and the third offspring being female. The probability of that event of having 3 females is equal to the probability of each one multiplied all together. I do want to note that order can matter. So if we were interested in a specific order, so let's say female, male, then female, then we calculate it as that probability multiplied together. So the probability of female times the probability of a male times the probability of a female. But if we were interested in just 1 out of 3 of the offspring being male, then that male can be either the firstborn, the secondborn, or the thirdborn. So order in that case does matter, and we have to account for that by counting up how many combinations. We'll work with this. As we get to the binomial distribution. Now let's do some genetics. So the first example, or some examples. The first example is from genetics, and you've probably seen this before, but we're going to set up a dihybrid cross and look to see what a Punnett square gives us, and then I'll show you how we can actually calculate the probabilities using our multiplication and addition rules, and also introduce you to this idea of a probability tree. Here's the example from genetics. Assume that we have 2 individuals that are going to mate. One individual is heterozygote at both A and B, and the second individual is a homozygous recessive at the A locus and heterozygote at the B locus. We want to know what's the probability of getting an individual that has big A, little b, little b. In biology classes, we learned how to do this using a Punnett square, and the Punnett square was formed based on the gametes that can be produced. So for parent 1, this individual could produce gametes big A, big B, big A, little b, big B, or little a, little b. Parent 2 is only going to produce 2 gamete types, little a, big B, and little a, little b. Then from here, we just go ahead and fill out the possible offspring genotypes that we could see. So in this example, we have a total of 8 possible genotypes that our offspring can have. Our interest is in a single genotype. we wanted to know the probability of that genotype. Well, there's only one option, one offspring that gives us this genotype, and we had 8 possibilities of genotypes for our offspring. So our probability is 1/8. Can we have done this using probability? Yes. It comes down to the gametes. So if we look at the individual loci, parent 1 can donate a big A 50% of the time. They donate a little a 50% of the time. They give a big B 50% of the time and a little b 50% of the time. Parent 2 is going to give a little a 100% of the time, a big B 50% of the time, and a little b 50% of the time. If we wanted to know this probability, well, we have to think about how this can form. In order to get the big A, little a, parent 1 has to give us the big A. And then parent 2 has to give us the little a. For little b, both of our parents have to give us the little b. The probability that parent A gives us the big A is 1/2. The probability that parent 2 gives us the little a is 1. Probability that parent 1 gives us a little b is 1/2, and probability that parent 2 gives us the little b is 1/2. Since all of these events have to occur in order to get this big A, little b offspring, we multiply our probabilities and we get the same answer as we did with our Punnett square. Using the same parent, we're going to ask a new question. What's the probability that our offspring is big A, big B, little b? Now we could look at the Punnett square that we created and come up with the answer fairly easily, but I'd like to show you another way of calculating probabilities using a probability tree. So with this probability tree, what we want to do is start and look at the options, the ways in which we can form our different offspring, or the genotype of our offspring. So we're going to start with parent 1. Parent 1 is going to give us either a big A or a little a. And it does so 50-50 chance. Parent 2 is always going to give us a little a. So that probability is 1. Now if we wanted to stop here and ask what's the probability of getting a big A, little a, all we have to do is look at the paths that we would need to take in order to get that genotype and multiply the probabilities along that path. But we're not done. We're actually interested in calculating the probability of our big A, little a, and big B, little b. So we have one already completed. We've got the A genotype completed. Now let's look at the B. Now with the B, our parent 1 can give either a big B or a little b, and it occurs at 50% of the time. Our parent 2 can give a big B or a little b, also at 50% of the time. Now we put the option on each path because each path represents a different possibility in which we can get our outcome. I don't need to go here because we've already reached our end. We know we don't want to know the probability of getting a little a genotype. So I don't have to complete that. Now, going across these genotypes, if we follow the path, we would get a genotype big A, big B, big B. This path gives us.
So we utilize some genetics examples to demonstrate working with probabilities. The genetics examples were used because you've likely been exposed to Punnett squares and calculate genotype frequencies in previous classes. But the genetics examples only represent a small subset of the various probabilities that we can calculate when doing research. So here's a couple more examples that'll give you time to practice calculating probabilities. We'll assume that we are working with fish in a stream. Of all of the fish in the stream, 75% are female, 25% are male. 50% of all of our fish are mosquito fish, 30% are shiners, and 20% are darters. We've got 5 questions. Question 1, if we catch one fish, then what's the probability that our catch is either a shiner or a darter? Question 2, if we catch one fish, then what's the probability that that fish is either a male or a shiner? Question 3, if we catch one fish, then what's the probability that that fish is female and either a mosquito fish or a darter? Question 4, if we catch 3 fish, then what's the probability that all of our fish are male? And lastly, our 5th question, if we catch 4 fish, then what's the probability that none of the 4 are mosquito fish? So pause this video and work out these probabilities. Try to work them out by hand using what we've learned for the addition rule and the multiplication rule. So now you've had time to calculate these probabilities. Let's work through them. So the first question is, what's the probability that we catch a shiner or a darter? Well, we catch one fish, and that fish can't be both a shiner and a darter, so our outcomes are mutually exclusive. When working with mutually exclusive outcomes, the probability of shiners or darters is equal to the sum of the individual probabilities. So probability of the shiner is 0.3 plus the probability of the darter 0.2. That means the probability that we get a shiner or a darter is 0.5. Question 2. What's the probability that we get a male or a shiner? Now this question's different. Now when we catch that fish, it can be both a male and a shiner, so we are dealing with not mutually exclusive events, and that changes our probabilities. So we still have the probability of being male. We're going to add that to the probability that that fish is a shiner, but with those probabilities, we've double counted the probability that we are both a male and a shiner. So we have to subtract that joint probability. So the probability of being a male is 0.25 plus the probability of being a shiner is 0.3 minus the probability that that fish is a male and a shiner. That number is 0.475. Question 3. What's the probability of being a female and either a mosquito fish or a darter? So with this question, we're asking what's the probability that we are a female and a mosquito fish, or probability that we're female and a darter. Now again, we can't be both a female mosquito fish and a female darter, so these are mutually exclusive outcomes. But female and mosquito fish are not mutually exclusive outcomes. They can occur together, so this is a combination. So our first probability of female and mosquito fish is multiplication rule. And the second part, female and darter, is also multiplication rule. But then by the addition rule, we add the two probabilities together. So female is 0.75, mosquito fish is 0.5, darter is 0.2. We add those numbers together and we get 0.525. Next question, what is the probability that we have all male and 3 fish? Well, the only way to do this is if we catch the male for the first fish, male for the second fish, and male for the third fish. This is simply the product of all of our probabilities of being male. So 0.25 cubed
which is 0.0156. Our last question, what's the probability that we have no mosquito fish in all 4 fish? So what we could do is kind of calculate all the different combinations where we catch at least 1 mosquito fish, or we can say we can do this if our first fish is not a mosquito fish, our second fish is not a mosquito fish, our third fish is not a mosquito fish, and our fourth fish is not a mosquito fish. Well, we didn't give you probability of not being a mosquito fish directly, but we can easily calculate it. As I said, the sum of our probabilities must be 1. If the probability of being a mosquito fish is 0.5, then the probability of not being a mosquito fish is 1 minus that amount. So, it's 1 minus 0.5 times 1 minus 0.5 times 1 minus 0.5 times 1 minus 0.5, which comes out to 0.5 for all of them, but we multiply our probabilities together and we get 0.0625.
So now that you've seen the answers, I have a homework assignment posted that'll give you even more practice at calculating these probabilities. I know this isn't technically a math class, but we have to understand how to work with probabilities so we could estimate and calculate expected frequencies or expected numbers later on in the course. Now we've talked about all of the events being independent of each other. So the probability of being male or female is independent of the species of fish. But what happens if that's not true? What happens if the probability of being male or female depends on what type of fish we're looking at? Well, that changes how we work with our probabilities. As an example, consider hair color and eye color. You've probably seen this example used in previous classes. This example is often used because hair color and eye color tend to be linked. They tend to be inherited together. So if we look at a population, we could see that a probability of being blonde-haired may be 25%, and the probability of being brown-haired is 75%. But then when we look at the probability of being brown-eyed, that probability tends to depend on what our hair color is. So if we have brown hair, then the probability of being brown eyes is 7/8. If we have blonde hair, then our probability of being brown eyes is 1/8. You can see that our probability of being brown-eyed changes based on our hair color. So what I want you to do is make a probability tree. We're going to start with hair color and then do eye color. Make sure you write the probabilities at each branch point and then calculate the probabilities for each path. Our goal is to use this probability to calculate the probability that we are blonde and have blue eyes, and then also to calculate the probability that we have blue eyes. So pause this video, take the time to make your probability tree, and come up with answers for these two probabilities.
So let's make this probability tree. We're going to start with hair color. So our option is that we can either be blonde hair or brown hair. Blonde hair occurs 25%. So 1/4 are blonde hair, 3/4 are brown hair. Our option for eye color is either brown or blue. And we can be blonde or blue, or brown or blue, regardless of our hair color. But the probabilities differ. So if we are blonde hair, then the probability of being brown-eyed is 1/8. Now, at this couplet, we have two options. We can either be brown eyes or blue eyes. That means that the sum of that couplet must equal 1. So if we have 1/8 brown eyes, then 7/8 is blue eyes. The same applies if we have brown hair. If we have brown hair, then the probability of being brown eyes is 7/8, which means blue eyes is 1/8. Now, if we look at actual probabilities, we've got blonde and brown, and that's going to be multiplication along our path. So 1/4 times 1/8, which gives us 1/32. If we are blonde and blue, we multiply along our path as well. So 1/4 for blonde, 7/8 for blue. So we get 7/32. We multiply along our path for brown and brown. So 3/4 times 7/8, and we get 21/32. And lastly, we have brown and blue. That's 3/4 and 1/8. That is 3/32. You will notice that the sum of all of these paths must equal 1, because we only have these 4 outcomes. Now, I asked you, what's the probability that we have blonde and blue eyes? Well, blonde and blue eyes is right here. That's our probability. So this is probability of blonde and blue. And we found it by making the tree and following our path, multiplying along our path. The second question is the probability that we have blue eyes. Now, we can't just go in and look at brown eyes without hair color, because the probability of our eye color depends on our hair color. But what we can do is look at all of our outcomes and say, well, we get blue eyes there, and we get blue eyes there. So the probability that we have blue eyes will equal the probability that we have blonde and blue eyes, or the probability that we are brown-haired and blue eyes. And that gives us 10/32, or 5/8, or I'm sorry, 5/16. 5/16.
When do we utilize dependent events? The examples that I'm going to show you all involve tests. So you go to the doctor, you get tested for something, the test comes back negative. When you go and ask that doctor, hey doctor, test comes back negative, comes back positive, what's the probability that I actually have whatever you tested for? Well, sometimes the doctors are going to say the test is X% accurate, and that means you have X% chance that you actually have it. And I'm going to show you that that's not true. Why? Because the probability that the test comes back a certain way depends on whether or not you have the condition. So for example, we're going to use the herpes blood test. This is a blood test that is performed after you donate blood. It's performed on the blood sample itself, and it's a fairly cheap test. So our question is going to be, if we test positive, what's the chance that we actually do have herpes? Well, before we can get to this, we need to look at some terms. So, if the test comes back positive, and we actually do have that condition, that probability is called the sensitivity. This is also our true positive. If the test comes back negative and we actually don't have the condition, that represents our specificity, or the probability of having the true negative. The other two situations are all of our false positives or negatives. So if the test comes back positive but we don't have the condition, this is our false positive. If it comes back negative and we do have the condition, this is our false negative. Now obviously we want to avoid our false positives and false negatives when developing our own tests, so we want to have sensitivities and specificities as high as we possibly can. I do want to point out that our probabilities have to sum to 1, But the probabilities that we're talking about is across the rows, the test results. So we're going to assume that our condition is known. We either don't have the condition or we do have the condition. If we don't have the condition, then our test results are either going to be positive or negative. Those probabilities are going to sum to 1. If we do have the condition, test result will also be either positive or negative. So those probabilities are going to sum to 1. So let's work with the actual numbers for this herpes blood test that the Blood Donor Center uses. According to this test, it is 91% sensitive and 92% specific. What does that mean? What do those numbers and terms mean? Well, if we are sensitive, that means we want to detect the condition when you actually have the condition. If you're specific, you want to actually not test the condition when you don't. So I like to think of the specificity and sensitivity as how well do we do at actually detecting the condition. Are we sensitive enough to where we can actually detect it? And are we specific enough so that we don't detect it incorrectly? So if we actually don't have the condition, we actually do get that negative test. Now, as I'll show you, the probability that the test comes back positive or negative depends on the number of individuals that are actually infected with herpes. So in the United States, about 57.7% of the population is infected with the herpes simplex virus 1 strain. We'll use that percentage in this example. So our first question is, what's the probability that we will actually get a positive test? Now with this question, remember that our probability of having a positive test is going to be dependent on our underlying condition. So either sometimes we'll have one probability of testing positive if we actually do have herpes, and we'll have another probability of testing positive if we don't have herpes. Once we calculate this probability, we will then answer question 2. So if we do test positive, then what's the probability that we actually are infected? This is the shorthanded way to ask that question. What's the probability that we're infected given that we do test positive? So this pipe symbol here literally means given that or provided that. So two things that we're going to do. We'll first calculate the probability of a positive test, and then we'll use that information to figure out the probability that we actually are infected. So let's look through what is given in our problem. So our condition is either HSV1, either we have it or we don't. If we don't have it, then the probability that we actually test negative is our specificity, which is 0.92. Our sensitivity is 0.91. That's the probability that we test positive and we actually have our HSV1. Now, as I said, the sum of these rows must equal 1. So, our false positive is 0.08, our false negative is 0.09. The other thing that's given in the problem is the percentage of the population that actually has HSV1. This is 57.7%. This means that the probability that an individual has HSV1, regardless of the test, is 57.7%. We will use this. Now, question number 1 asks, what's the probability that we test positive? And I'll use P plus sign to represent testing positive. Well, if we're going to test positive, then we've got two situations when we test positive. We can test positive when we actually have HSV. So, in order for that to occur, we have to first have HSV, then we have to test positive given that we have HSV1. Note the pipe symbol here to represent given that. That indicates that our probability is dependent on some underlying condition. Alright, so we can have HSV1 and test positive. We can also not have HSV1, yet we still test positive. This is our false positive. So not HSV1. Alright, so what do we have here? Well, the probability that we have HSV1 is given in the problem. And it should always be given in the problem. The probability that we test positive, given that we have HSV1, well, that's our sensitivity. The probability that we don't have HSV1 is 1 minus the probability that we actually do have HSV1. Because, again, our outcomes or possibility is that we have HSV1 or we don't. The sum of those probabilities must equal 1. And then lastly, probability that we test positive but we don't have HSV, that's our false positive. False positives. So now we already have all of our probabilities. We can just plug them into our equation. So I get 0.52507. That's the probability that we test positive and we have HSV1. And 0.03384 is the probability that we test positive and we do not have HSV1. Sum of these is our probability that we test positive, which is 0.55891. So, in the general population, if you take a random individual and give them this blood test, we have a 58.9% chance that that test comes back positive. That's what this number tells us. Question 2 asks, if we test positive, then what's the probability that we actually do have HSV1? Well, what we have to look at is we're looking at the proportion of all of the positive tests that actually correspond to those individuals that have HSV1. So what we're looking at is saying we know our total, what proportion of those actually have HSV1. So this probability is the probability that we have HSV1 and we test positive for it. And we're going to divide it by all of the times we test positive. And all of the times we test positive is both our times we have HSV1 and the times we don't have HSV1. So I'm going to plug in our numbers that were given in our problem or that we calculated. And we see that the probability that we actually have HSV1 if we test positive is 0.939. So we have 55.9% of the population is going to test positive. When they do test positive, you have a 93.9% chance that you actually do have HSV1. Calculating our probabilities for that herpes blood test demonstrates or allowed us to derive Bayes' theorem. Bayes' theorem basically gives us the probability that we have a condition given some underlying test. In mathematical formation, it's these two equations. So the probability that we have A given that B happens is equal to the probability that we first have B and we have our condition divided by all of the times we have B. Now, all of the times we have B is the denominator for this second condition. So all of the times we have B, we can get B whenever we have A occurring. and we can have B whenever we don't have A occurring. Now, this could be a little bit confusing, and that's why in the example I wrote out the tests. Either you test positive or negative, or you test positive or negative, and you test positive or negative regardless of whether you have the condition or not. I do want you to know these equations. I'll give you these equations on the test, but you need to know how to use them. So here are some practice problems. We've got a lot of different examples where where the doctor runs a test or we perform a test, and that test, the probability that it comes back positive or negative depends on the underlying conditions. So we've got two different tests. The first is this quad test. This quad test is performed or can be performed later in pregnancy. So what will often happen is you have a basic test, and based on some measurements, based on another test, they say, well, your child may have Down syndrome. And then you may be recommended to go ahead with this additional test. Now, this quad test has a lot more risks, and what we're going to see is how good is the test? If this test actually comes back positive, then what's the actual probability that our child will have Down syndrome? So here's our important statistics for the test. This test is 81% sensitive, and it gives a false positive rate of 5%. The probability that we actually have Down syndrome, or that a child is born in Down syndrome, is 14.47 out of 10,000 births, or 0.1447%. Now, I'll note that this is just an average because Down syndrome, the risk of Down syndrome, actually increases as the age of the mother increases. We're just taking an overall average. So using this information, calculate the probability that our child has Down syndrome if the test does come back positive. So pause the video, work out this probability, and then we will check your answers before moving on to a second type of tests. So here's the work for calculating the probability that you actually have Down syndrome if the quad test came back true. So what I've done is wrote down everything that was given in the problem, and I did this in black ink. So I said we have 81% sensitivity. That's when you have the condition that you actually test positive. And I gave a 5% false positive rate. So you don't have the condition, yet you still test positive. I then filled in the corresponding numbers in blue for our specificity, which is 0.95, and our false negative rate at 19%. What's the probability of having Down syndrome? Well, that was also given in the problem. The rate that we use is 0.1447%, which translates to a chance of 0.001447. Now, I'm also going to calculate the probability that you don't have Down syndrome, and that's just 1 minus the probability that you do. So that answer is 0.998553. Now remember, we're going to use both the probability that you have Down syndrome and the probability that you don't in order to calculate the probability that we get a positive test. So that's first. What's the probability that we get a positive test? Well, that equation is all of the times we have Down syndrome and test positive, and all of the times we don't have Down syndrome but we still test positive. So we account for the probability of having Down syndrome and testing positive, and we're going to add that to the probability that we don't have Down syndrome, yet we still test positive. So the probability that you test positive is actually pretty small, 0.0511, or about 5% of these tests will come back positive.
Using this information, we then proceed to the next part of the question, which is, what's the probability that you actually have Down syndrome if you test positive? Well, again, for that answer, what we're saying is, of all of the times we test positive, what proportion of them represent times we have Down syndrome? So that's the probability we have Down syndrome times the probability that we test positive when we have Down syndrome, divided by probability of testing positive. These are the same numbers. These numbers are the same numbers that were used in the problem above. So to calculate the probability that you tested positive, and that was our answer for the probability that we tested positive. So if the test comes up positive, you still only have about a 2% chance that you have Down syndrome. Now that sounds crazy. Why would you do this test if it's that low? Well, this test isn't recommended for all cases. In some cases, if you show other high risk situations, then they will recommend you taking the test. So how does that change our answers? Well, let's take a look at our graphs. When we performed this test, we assumed we had a very low incidence of Down syndrome. Now this is the average, and it's representing the average right down here, where we have the lowest risk of Down syndrome. But what if our mother is over 40? Well, the incidence rate is now more than 120 out of 10,000 births. That changes the probability that we actually have Down syndrome. Here's the question. Does that change the probability of having Down syndrome if we test positive? Try it out. Let's assume we have 120 out of 10,000 births. That is our probability of having Down syndrome. So if we do 120 divided by 10,000, we're going to say it's 0.012. That's our probability of having Down syndrome. If the probability of having Down syndrome. So now just go ahead, repeat the problem, but in place of this probability, use 0.012 as our probability of having Down syndrome. So here's our quad test work again. What I've done is inputted in the new numbers using probability of having Down syndrome of 0.012. In red ink, I put these numbers. So for the probability of testing positive, I substitute 0.012 for our old probability, and I also correct the probability that we don't have Down syndrome. So that's 1 minus 0.012. For this part of the problem, probability of testing positive is increased to 0.05912. That's not a large percent increase at all. It's actually fairly small, less than 1% increase. However, we see this big effect on our probability that we actually have Down syndrome if we test positive. So again, I substitute the numbers, those are in red, and I get our new probability of having Down syndromes if we test positive is 16.44%. That's a big increase. Now it's starting to make sense why this test has stayed around. It's still not perfect, and the doctors won't use age as the only indicator to recommend this quad test. They'll look at some other things, including width of the spinal cord and some morphometrics of the developing fetus. So taken together, we can drastically improve our probability that we actually have Down syndrome if the test comes back positive. So we worked through the quad test problem. Now let's try to work through one more. This was actually a paper that came out several years back. The focus was to create a quick method
of detecting cocaine in somebody's body. What the authors wanted to do was to develop this quick test so that police officers can have it in their vehicle, and if they suspect somebody is driving under the influence, then they could perform this quick test and either arrest them if they are high on cocaine or let them go. So, in this test, and it's reported in the paper. You can download it here. Here's our citation. That test is reported to have a sensitivity of 92.2% and a specificity of 84.4%. In this study, they had 602 cocaine negative individuals and 866 cocaine positive. Now, these numbers, the negative and the positives, were determined by a blood test, which is very, very good. So, assume that these are true. Now, if we assume that this is our rate in our regular population of individuals, then what I want you to do is calculate the probability of the cocaine test coming back positive. And then once you do that, move to question 2 to answer what's the probability that you are not on cocaine if this test actually does come back positive. Pause the video, work out this work, come up with the probabilities, and then we can check our work. Here's my work for the Cozart cocaine test. Like I did before, in black, I gave the numbers that were in our problem, so we knew the sensitivity and the specificity. And then I had to fill in our false positives, and I also filled in the false negatives, although we don't really use it. I also calculated the probability that we're actually on cocaine, and that's information given in the problem. Then in blue, I went ahead and calculated the probability that we're not on cocaine, which is just 1 minus 0.59. Using these numbers, I then calculate the probability that we will test positive. Filling in our numbers, I get 60.8% chance that the test comes back positive. Now the question is, what percentage of that is when you're actually on cocaine? So that's our probability that we're on cocaine if we test positive. Filling in those numbers, we see that we're 89.5% likely to be on cocaine if we test positive. Is this 100%? No. Why not? Well, we've got false positives. And the number of false positives and true positives is dependent on our underlying proportion of cocaine users in our population. So if we were working on a test, if we were trying to develop one of these tests to try to detect some underlying condition, and we wanted to really improve our test, then we should be focusing on trying to reduce our false positives, trying to maximize our sensitivity, and we want to make sure that we have a sizable portion in our population that our true positives actually swamp any sort of false positive. What's the practical nature of this? Well, a question that has come up is pregnancy tests. Pregnancy tests are the same thing. They can test positive, they can test negative. They've got false positives, they have false negatives. What does that mean if it comes up positive or negative? Can we trust the results? Well, here's what we know. You can dig up the actual numbers, sensitivities and specificities, and what you will see is that if the test comes back positive, you're over 99% likely to be pregnant. It's that good of a test. If it comes back negative, that's where you still have the possibility of being pregnant. So just because it comes up negative doesn't mean that it is negative. Usually, that's where the errors in reading the pregnancy test come into play. They didn't do it correctly, so they get a negative, or they misread a negative. You don't misread positives. So if any of you are trying to have kids, or if you're wife, girlfriend, significant other, for all the males out there,
are having kids and the pregnancy test comes back positive, hey, stop there. It's positive. And that goes for even the cheap $1 pregnancy tests. They're really, really good. So we use Bayes' theorem to calculate probabilities that we actually have a condition if the test comes back positive. And this is extremely important, and it's something that you should understand anytime you have some tests performed. But Bayes' theorem also applies to doing statistics. Right now we have a new method called Bayesian statistical methods, or we can do the old frequentist approach. Before we talk about these, I don't want to say that one's better than the other, but I do want to expose you to Bayesian statistics. So our old approach, the frequentist approach, is based on probabilities. So what we do is make inferences based on repeated sampling. We try to fit those to probability distributions, and these distributions allow for fluctuations in our knowledge because it knows that if we repeat the sample, we can get a slightly different answer. But this is a static method, and by that what I mean is that our population parameters are assumed to be fixed, and that the only variation that we have is due to the randomness of our sampling. Bayesian method is more fluid. It doesn't make that assumption of our fixed parameters. Instead, it assumes that our parameters can actually change, that they vary. How does it approach this? Well, the Bayesian statistical methods, instead of coming up with a probability or a p-value, utilizes something called a likelihood. And what this likelihood means is that we're trying to quantify our belief in something based on prior or previous knowledge and experience. So if we have some prior knowledge, we use that as our foundation for the current experiment. Then this experiment that we do today serves as previous or prior knowledge for experiments done tomorrow. And what we keep doing is estimating or revising our estimates in such a way that we hope to kind of approach a true situation. That's what we mean by it being more fluid. So here's an experiment. So let's say we're studying herpes simplex virus again, and we're studying the prevalence in our populations. We go out and do repeated samples of populations, and we get different prevalences. So we go out and we sample this year, we sampled last year, and we sample 2 years from now. Our frequentist approach would say that our population parameter, so the population prevalence, remained constant from year to year, but any variation that we have is just due to random fluctuations in our sample. Bayesian approach is going to say, no, our prevalence probably changed every year. We don't know what it is, but every time that we resample, we have a better and better idea of the variation and the central tendency of those parameters. So with every sample that we take, we ultimately revise our predictions of the true population parameter. Again, we're not saying that this is definitively the population parameter. Instead, we assign likelihood values to say, well, I'm this confident that the population parameter falls within a certain range. So what does this mean for us? Do we need to worry about this for any of our exams? No. I present the frequentist versus Bayesian approach for completeness. There are some fields that utilize Bayesian statistics quite a bit, including some phylogenies or systematics, and I think psychology is trying to push Bayesian statistics. But it's been my experience that the Bayesian statistics end up arriving at similar answers as the frequentist approach. And yet the Bayesian analysis is much more complicated to comprehend, much more complicated to explain, and it usually takes some specialized programs, or at least some special programming skills, in order to get it to work. So I ask you, if you have an easy way or a hard way to come up with the same answer, what would you prefer? Me, I think I'd take the easier way.